Hello everyone, my name is Wenqian Dong. I'm from University of California, Merced. In this talk, I will introduce our project, SmartPGsim, using neural network to accelerate the SC'20 problem. This work is cooperated with the Pacific Northwest National Laboratory. So the power grid simulation is a very important HPC application to study the management of power flow on each generator. But the thing is, it involves solving a very complex nonlinear optimization problem, the SC'20 problem. The SC'20 problem is the most fundamental and time-consuming part in the power grid simulation. The problem size of SC'20 is generally large, which means this problem is mission critical. And the problem is, we still need to frequently use we still need to repeatedly solve the SC'20 problem multiple times and require a real-time updates. So the SC'20 problem can be formulated as an objective function, the fx, which is subject to some physical constraints. As we can see, the Gx equal to 0 is the AC power law, which is to make sure the power grid system is always stable throughout the whole simulation. And the Hx are power limitation on the transmission line. We will take these equality and inequality equations as our variable constraints. In the solving process, we will convert this formulation as a solvable format, the logarithm equation. While the equation is a large linear system and usually involves a large number of iterations. The neural network has been used for a tool to learn and model the complex linear and nonlinear relationship between the input and output data sets. Scientists have shown some preliminary success in these HPC applications, like the traffic management, weather prediction, and etc. We also want to introduce the neural network-based approximation to benefit the power grid simulation. But the thing is, we have some challenges. First, how to do the feature selection. The HPC application usually involves complex and high-dimensional data structure. How to efficiently sample those data at the appropriate select some features for the neural network input and output. Second, the accuracy requirement of the power grid simulation is generally high. How to apply the neural network to the SC'20 simulation without disturbing the simulation robustness is a big challenge. Third, there are no systematic approach to build the neural network model by users. Domain scientists will have no such background of machine learning to build the machine learning model by themselves. At last, the machine learning model usually is taken as a black box without interpretability. How to impose these physical constraints into neural network to ensure the wideness of neural network prediction is challenged. The existing work to solve the SC'20 problem is using a numerical solver. Here we use MIPS in the math power. The solver will start with an initial point, which might be far away from the final solution. Then the solver needs to iteratively refine the solution until it converges. In this study, we will use the SmartPGsim, a framework that can facilitate the construction of a neural network model to accelerate the SC'20 simulation. It uses neural network to predict a high-quality initial point, and then it will inject these good initial points into MIPS to let the simulation converge quickly. Through the combination of the machine learning method and the numerical solver, we can 100% guarantee the feasibility of our final solution. Here, I will introduce our framework, SmartPGsim, in details. So the framework introduces some offline phases and the online phases. During the offline phases, the SmartPGsim will take some candidate features as input, and then it will perform a sensitivity study to guide the design of the neural network topology. Based on the observation in the sensitivity study, we can introduce a multitask learning model, which is using some which is trying to use some layers to enable the information sharing, but will also develop some customized design for each task. Meanwhile, in the multitask learning model, we will incorporate some physical laws and constraints to facilitate the model interpretability. After the offline phases, we will have a multitask learning model ready for a hybrid approximation. At the runtime, the SmartPGsim will use the prediction of the multitask learning model as a warm start point and use the numerical solver MIPS to guarantee the feasibility of our final solution. I will explain these components one by one. So in the sensitivity study, we will analyze the impact of candidate features by varying the precision of the data set. Here we introduce two data types, the imprecise default data and the precise simulation data. The imprecise default data is the default value at the initial point in MatPower, an open source framework for the power grid simulation. And the precise simulation data is the exact solution collected in the numerical solver MIPS. Also, we will take this as our ground truth to do the neural network training. So, as showed in the right figure, we will inject the imprecise and precise simulation data into the code region, and then we will collect the performance results, which are the success rate and the speed up. We will use the performance results to analyze the sensitivity of each variable. So the interesting thing is, through the sensitivity study, we can observe two properties of the candidate features. The first thing is, these candidate features showed some diversity and dependency. Different variables have different impacts on the success rate and speed up. Also, these features have implicit dependency between each other. Some variables, they must work together to improve the simulation accuracy. So based on the property of diversity and dependency, we introduce an interactive learning model in which we will use our multitask learning model as our basis and develop a domain-specific design on the multitask learning model. The multitask learning model will take some fully connected neural networks in the shallow layer to enable the information sharing between tasks. In the shared layer, the parameters are shared with some connected neurons, and all tasks will share the common loss function. The loss function is used to guide the model training for accurate outputs. Also, we will apply some customized design for the neural network topology to each task. Such task-specific design can satisfy the diversity requirements. Also, we will apply a domain-specific design for the multitask learning model. We classify our tasks as main tasks and auxiliary tasks. So in the model training, we will focus on the main task X, and we will use the auxiliary tasks lambda mu Z as an augmentation to provide some additional information for the main tasks. So besides that, we will take the computation dependency in the numerical solving process to design our model topology. Also, to make our model is more understandable, we will incorporate some physical information in our model. In the power grid simulation, the solution must respect some specific physical constraints, like the power grid generator constraints, line flow constraints, and the box voltage constraints. By incorporating these physical constraints into the multitask learning model, not only improve the model accuracy, but also increase the model interpretability. We will incorporate these physical constraints by adding the soft and the hard constraints into our models. The soft constraint is adding some physical information into the loss function to get the neural network training. The hard constraint is applying activation functions in the model to restrictly bound the output range. Here I will give an example of embedding AC power loss into the soft constraint. First, we will transform the original ACOPF power law as an absolute format, and we will take this absolute format in the loss function. Then, during the model training, the loss function is manualized to guarantee the feasibility of the AC power law. Here, we can see the equation provides some domain information, which is the CG and Y buses. The Y buses represents the power grid bus topology, and the CG is the resistance information about the power grid system. So these two physical information will guide the model training to improve the model accuracy and feasibility. In our paper, we will add 4 soft constraints in total, and you can find more details in our paper. Also, we will add some hard constraints on the variable z and mu to guarantee these two variables will always greater than 0, which is satisfy the inequality constraints on the variable z and the mu. So as our evaluation, we will conduct our simulation based on the NVIDIA Tesla Volto GPUs. We will use 5 IEEE bus system as our test cases, and we generate training and validation data by the MatPower, which is the open source framework of the power grid simulation. So here, we will evaluate our model speed up and accuracy of SmartPGsim. The left 2 figures shows the comparison of the SmartPGsim and the MIPS model. We will use different power bus systems, and we can see in all test cases the SmartPGsim performs better. It achieves 2.6 speed up and fewer iterations of simulation convergence. Also, for the success rate, we can observe that the output of SmartPGsim is closer to the target value, the success rate achieved by the numerical solver MIPS. So these 2 observations reveal that the SmartPGsim can achieve a speed up without having too much failure cases. Firstly, to show the prediction accuracy of our multitask learning model, we will show the validation of quality loss. We compare the accuracy of the SmartPGsim with the exact solution in the MIPS. All variables will be normalized to the range 0 to 1, and we will use the x-axis to show the prediction value of SmartPGsim, and the y-axis is the ground truth value. As we can see, if the prediction in the SmartPGsim is perfect. So all points will be lying on the y equal to axis line. And as we can see in these figures, all prediction in the SmartPGsim is very accurate and consistent. It has small variation on the quality, on the prediction quality. And at the end, we also analyze the effectiveness of the multitask learning and the physical constraints. We use the SAP model to represent separate neural network models, which is trying to show the efficiency of the information sharing. And also to show the efficiency of the physical constraints, we will remove the physical constraints in the MTL model. As we can see in these two figures, the speed up and the success rate are gradually improved by enabling the information sharing and the physical constraints. So at last, we can draw a conclusion that using the combination of machine learning and the numerical methods can be powerful. Utilizing the neural network topology will bring large performance improvement, and using numerical method can guarantee or solution is always feasible. Here we introduce a framework, the SmartPGsim, which is a hybrid method of the machine learning and the numerical solver. So by doing so, we can accelerate the power grid simulation without losing any optimal. So inside the SmartPGsim, we can see we use a multitask learning model to for the information sharing and the customized design, which is very good if we have some if we have multiple tasks in our simulation. And also we enable the model interpretability by adding some physical information instead of using a black box. And as a performance perspective, the SmartPGsim is 2.6 times speed up and up to 3.26 times speed up, compared with the traditional numerical solving process. Over 10,000 problems without losing the feasibility and the optimality of the final solution. Thank you so much for listening. If you have interest in our paper, you can download our paper on arXiv, or if our paper available afterwards. And you are welcome to visit our homepage and learn more about the earlier project at PNL.